In example number 3, we're going to start to see here why it's so important to be able to actually set up our integrals for surface area with both a dx and a dy direction. To see why, let's jump into the details here. We're going to be working with the curve y equals a quarter x squared minus a half natural log. X is going to range from 1 to 2. And notice we're going to rotate this around the y-axis. Now, I have no idea what this curve looks like, but let's just say for the sake of argument that on the interval from 1 to 2, let's just say, again, for the sake of argument, let's just suppose that our curve looks something, I don't know, kind of like this. Something like that. Well, if I wanted then to go ahead and rotate this around, I find my mirror image duplicate, and I rotate like this, and I go something like this, right? And so I have a surface area along the outside, and it can be as shaded in kind of like by this blue stuff. Okay, so let's suppose that's what the shape looks like, at least very roughly. Now again, what I'll see is that my frustums here are stacking in a vertical direction. So it would be very important for me to be able to go ahead and demonstrate, not to demonstrate, but to be able to find So as I can see here, this particular function, when revolved around, is going to be... So after I have this picture, I can see that my frustums are going to be stacking vertically. Now what that means is that this should be set up as a default dy problem. So I'll write this down. Oops, and let me change back to black. Since our frustums stack vertically, this is, by default, a dy question. However, what that's going to require that we do is to take this equation and solve it to say x equals, which of course is very simple to do, and so I'd like you to pause here for a moment and see if you can figure that out. Ready, set, go. Okay, with almost like half a second of looking at that equation, you could probably start to see that that's going to be really difficult to solve for x. Because not only do you have the x squared that's sitting up there, but you also have this natural log of x, it's just going to be a headache. So while dy is the default way to set this up, it would be way nicer if we could go ahead and confirm, or if we could go ahead and show how to set this up as a dx question. So I'll write that since solving for x is difficult, or maybe even impossible here, we will set this up as a dx question. Of course, I'll still have to go ahead and do all of my different checks. So let's see quickly what we have. On the interval from 1 to 2, I need to go ahead and make sure that this function is definitely going to have a continuous first derivative and is going to be non-negative. Now to do this, I can easily just go ahead and switch over to a calculator to graph this. Now over here, what I can see is that if I was to type in my function, which is 1/4 x squared minus a 1/2 natural log of x, if I hit the graph button, I can see that on the interval from 1 to 2, very clearly my function does not go negative. And so I'm really happy with this. If I swap back, I'll go ahead and write this. Clearly, y equals a 1/4 x squared minus a 1/2 natural log of x is non-negative on the interval from 1 to 2. And we can also start by checking the derivative, which would be 1/2 x minus, notice here I would get 1/2x, because the derivative of my natural log is 1/x. Now, just like we did in the last section when checking for continuity, it's oftentimes easier to see this if I can combine this all into one fraction. Notice that my first fraction here is technically x over 2 if I put that x into the numerator. And so by multiplying that first fraction by x over x, I can get a common denominator very quickly. And so I can see here right away from this that this is only going to be undefined when x is going to be equal to 0. And so I can say that y prime is definitely continuous on the interval from 1 to 2. So that works out really nicely. Now I can go ahead and I can think about how I would set this up in a dy direction and in a dx direction. So really quickly, let's set up at least the template for dy. I would know that in dy, I would have something like the following. I'd have an arc length piece with the dy, and then over here, I'd have this kind of like g of y formula, right? It would be whatever x was equal to, that's what would go right in here. But now I can go ahead and start to see that if I want to swap this over, I can swap each individual piece. So I'll swap my differential to a dx and remeasure my arc length. I'm going to have 1 plus my derivative, which I'll just rewrite in this form. That's all squared. I would have my bounds that go from 1 to 2, and then I would have to change out this. But remember that if there was a x equals g of y that I could find, then g of y could just be replaced again with the value of x. And I actually have here a fairly simple integral to go ahead and work with. I'm not going to go through and evaluate it here, but I'd leave it for you to go try to evaluate on your own. It's very similar to a question that we did in the last section. It'll be much easier to see how to do this if you start by first going ahead and multiplying out this quantity under the radical and attempting to simplify a bit. You do not need a u substitution in order to complete this problem.